In this video, you will learn how to solve for UT, the displacement time history, for when the damping in the structure is 0. You will learn how to use the result presented in the review of complex numbers to solve the governing equation of motion. We begin by transforming the equation of motion. We can now apply our trial solution, UT, which we said was equal to G times by the exponential of ST. We can apply this to our equation of motion to transform it into a root finding problem. Recall that the equation of motion for an undamped free vibration problem is given by mu.t plus k ut equal to 0. More generally, if we include damping, this is equal to mu.t plus c u.t plus ku t equal to 0. Since we have information on our trial solution UT, we can also differentiate this the appropriate number of times for substitution into equation 2. u.t is equal to s times by g and the exponential function st, and the second derivative is just equal to s squared g times by the exponential function st. So substituting this into equation 2, we get s squared times by m plus sc plus k times by g times by the exponential of st, and that's equal to 0. If we then divide through by m times by g exponential st, this then gives us s squared plus sc over m plus k over m equal to 0. We can then define the quantity omega squared as being equal to k over m. This is an important quantity, as omega, which is equal to the square root of k over m, is what we call the natural frequency. Substituting equation 6 into equation 5, we then have s squared is equal to s squared plus s over m times by c plus omega squared is equal to 0. We can see here that this is a quadratic equation, so we have two possible solutions, s1 and s2. For the undamped case, we can say that c is equal to 0. As c is equal to 0, equation 7 now becomes s squared plus omega squared equal to 0. So this means that s squared is equal to minus omega squared, and our two potential solutions, S1 and S2, are equal to either positive or negative times the square root of minus 1, that all being times by omega. And as we know the square root of minus 1 is equal to I, that then gives us plus minus I omega. So this clearly has two solutions. If we remember equation 6 from video 2, we said that a solution for the type of system we are analysing can be expressed as g being equal to g bar exponential I theta. If we now define theta as being equal to omega t, and we note that we are seeking two solutions, then we can say that ut is equal to g1 times by the exponential function I omega t plus g2 times by the exponential function minus I omega t. Using our knowledge of complex numbers, we need to find values for g1 and g2 and transform this into trigonometric form. To obtain a general solution to the undamped case, we need to firstly relate g1 and g2 in equation 11, and secondly, we need to make use of Euler's transformation. From equation 4 in video 2, our first observation in equation 11 is that g1 is equal to g1r real plus I times by g1I, and g2 is equal to g2 real plus I g2I. If we then substitute equations 12 into equation 11, we then get ut is equal to g1r plus I times g1I times by the exponential function I omega t plus g2r plus I times g2I times by the exponential function minus I omega t. If we recall from Euler's equations that the exponential function of I theta is equal to cosine theta plus I sine theta, and the exponential function of minus I theta is equal to cosine theta minus I sine theta. Then we can write equation 13 as ut equal to g1r plus I g1I times by cosine omega t plus I sine omega t plus g2r plus I g2I times by cosine omega t minus I sine omega t. We then just need to factor out the imaginary number I, so that gives us ut is equal to g1r plus g2r times by cosine omega t minus g1I minus g2I times by sine omega t, and then our factored imaginary term I times by g1I plus g2I times by cosine omega t plus g1r minus g2r times by sine omega t. This is what we call the imaginary term. We want the imaginary term in this equation to vanish, as for engineering applications we are only interested in real values. To achieve this, we make the following definitions. Firstly, that g1I is equal to minus g2I, which we will define as just being gi, and g1r is equal to g2r, which we will define as being equal to gr. Equation 13, returning to equation 12, we can then say that g1 is equal to gr plus I gi, and g2 is equal to gr minus IGI. If we just compare this to equation 12, we can see that we've just replaced our definitions for G1R and G2R as we defined in equations 16, so we now have this simplified form which we've shown in equation 17. With this, equation 13 now becomes ut is equal to gr plus I gi exponential I omega t plus gr minus I gi times by the exponential function of minus omega t . If we now apply the Euler transformations again, we end up with ut is equal to gr plus I gi times by cosine omega t plus I sine omega t plus gr minus I gi times by cosine omega t minus I sine omega t. Expanding it out then, equation 19 in collecting terms, we end up with ut equal to gr cosine omega t plus gri sine omega t plus I gi cosine omega t plus I gi I sine omega t plus gr cosine omega t minus gri sine omega t minus I gi cosine omega t plus I gi sine omega t. We can then see that this term here and this pair of terms here, these both cancel. So we can then see that this is reduced down to ut equal to 2 times gr cosine omega t minus 2 times gi sine omega t. Noting that 2 times gr and minus 2 times gi are basically just constants that we haven't really determined yet, we can now just define these as being a equal to 2 times gr and b being equal to minus 2 times gi. This means then that ut can be rewritten as a cosine omega t plus b sine omega t. And this is a very important result. We can now say that the general solution to the equation of motion of free undamped vibrations, which we said was mu dot dot t plus kut equal to 0, is given by equation 21, which is ut being equal to a cosine omega t plus b sine omega t. The only remaining task now is to apply what we call the initial conditions to determine the constants a and b. To initiate any kind of motion in a free vibration problem, the mass of the system either has to be released from a known non-zero initial displacement or suddenly released from a known initial velocity. A combination of the two is possible. We can use knowledge of these to determine the coefficients a and b in equation 21. The formal statement for these initial conditions is given by u of 0, or the displacement at time 0, and the velocity at time 0. We note that we have to evaluate a derivative to apply the velocity initial condition. So if we take the first time derivative of equation 21, we end up with minus omega A times by sine omega t plus omega B times by cosine omega t. Then all we have to do is to evaluate equations 21 and 22 at time equals t equals 0. Doing this, firstly our displacement equation at t equals 0, everything cancels apart from the cosine term, so that leaves us with u0 equal to a. For the initial velocity, we have omega b, which means then that b is equal to the initial prescribed and known velocity divided by omega, which is the natural frequency. So our solution now becomes ut equal to u0 cosine omega t plus the initial velocity divided by omega sine omega t. So since omega squared, which is k divided by m, or omega equal to k over m, this is known. This is a known property of the structural system. Also, our initial displacement, that is known, and our initial velocity is also known. Then we're in a position to completely specify the response of this problem using equation 23. So for a known initial velocity and initial displacement, the response sketched out would look like following. Where we have an initial displacement u of 0, which in this case might equal 1, and we have an initial velocity, which is just the slope. That's also, in this case, assumed to be equal to 1.